And now in this lecture I'll answer two questions. In the first question we'll find out the area of this green shape, and in the second question we'll find out the length of line segment PQ that equals to x. We have to find out the value of x. So we start with the first question. In the drawing we have this small circle inside this big semicircle. We also know that this is line segment AQ, is equals to 4 units in its length. This is line segment TB, is equals to 1 unit in its length. This is angle STB, that is a right angle. This is angle PQA, this is also a right angle. Again, our task is to find out the area of this green shape. So first of all, we will define the radius of the big semicircle as x and the radius of this small circle as y. In addition, we will define the center of this small circle. This point is point O, and we will define the center of this big semicircle. This point is point C. We will define the point of tendency of tangent AB with this small circle. This point is point N. Likewise, we will define the point of tendency of tangent ST with this small circle. This point is point L. We define the point of tendency of tangent PQ with this small circle. This point is point H. And finally, we will define the touching point of this small circle with this big semicircle. This point is point K. In the next step, we will join points O and N together by a straight line. Point O is the center of the small circle, point N is the point of the small circle itself, therefore ON is the radius of this small circle, that is equals to y units according to our definition. The radius ON, that is equals to y, the radius ON is drawn to point N, that is the point of tendency of tangent AB with this small circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius NO. If AB is perpendicular to NO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. This is angle PQA, that is a right angle according to what is given us the question. AB is the diameter of this semicircle, and therefore it is absolutely a straight line. So if you focus on the upper side of the straight line AB at point Q, here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 states that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the upper side of the straight line AB at point Q? We have this angle that is right angle plus this missing angle, so that the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. Likewise, we focus on the upper side of the straight line AB at point T. Here the sum of the angles must be equal to 180 degrees according to rule 3. So which angles we have at the upper side of the straight line AB at point T? We have this angle that is a right angle according to what is given in the question, plus this missing angle, so that the sum of those two angles must be equal to 180 degrees according to the sum rule, rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. In the next step, we will join points O and L together by a straight line. OL is of course the radius of this small circle that is equals to y. Again, the radius OL that is equals to y, the radius OL is known to point L, that is the point of tendency of tangent ST with this small circle. And whenever you have a radius that is known to the point of tendency, then tangent ST will be perpendicular to the radius LO. If ST is perpendicular to LO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to the same rule, rule 1. So inside the quadrangle OLTN, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this fourth missing angle, in total it must be equal to 360 degrees. According to the rule that the sum of the angles in any quadrangle is equal to 360 degrees. And therefore this fourth missing angle must be equal to 90 degrees in its size. So inside quadrangle OLTN we have 4 right angles. And according to rule 5, any quadrangle that has 4 right angles must be at least a rectangle if not a square. So in order to quadrangle OLTN, it's a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle OLTN, side OL must be equal to the opposite side TN. But OL is y, therefore the opposite side TN must be also equal to y units in its length. In the next step, we join points O and H together by a straight line. OH is of course the radius of this small circle that is equal to y. The radius OH that is equal to y, the radius OH is known to point H, that is the point of tendency of tangent PQ with this small circle. And whenever you have a radius that is known to the point of tendency, then tangent PQ will be perpendicular to the radius AO. If PQ is perpendicular to AO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to the same rule, rule 1. So inside quadrangle OH QN, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this fourth missing angle, in total must be equal to 360 degrees according to the rule that the sum of the angles in any quadrangle is equal to 360 degrees. And therefore this fourth missing angle must be equal to 90 degrees in its size. So inside quadrangle HO and Q we have 4 right angles, and according to rule 5, any quadrangle that has 4 right angles must be its rectangle if not a square. So we know to quadrangle HO and Q is a rectangle because it has 4 right angles, but we also know that the opposite sides of a rectangle are equal to each other. So in rectangle HO and Q, side HO must be equal to the opposite side NQ. But HO is y, therefore the opposite side NQ must be also equal to 1 unit in its length. This is line segment QT. Line segment QT is part of the straight line AB. AB is a diameter, it is absolutely a straight line. QT is part of the straight line AB, therefore it is also a straight line. So QT is a straight line, and therefore QT must be equal to Qn plus Nt. That is to say QT must be equal to Qn, that is y, plus Nt, that is y. So in total Qt must be equal to 2 y units in its length. AB is the diameter of the semicircle. The radius of the semicircle equals to x. The radius of the semicircle equals to x, therefore the diameter must be equal to 2x. So the diameter AB equals to 2x. From one side, but from the other side, the diameter AB also equals to AQ plus QT plus TB. Again, the diameter AB in total equals to AQ plus QT plus TB. So I write it down. AB, the diameter AB equals to AQ plus QT plus TB. And again, if you found out that the diameter AB of the semicircle, from one side it is equals to 2x, it is twice as long as the radius, but from the other side it also equals to AQ plus QT plus TB. So 2x equals to AQ is 4, according to what is given as the question, plus QT. We just like now found out that QT equals to 2y units in its length, plus TB. TB equals to 1 unit in its length, according to what is given as the question. So in total, we actually found out that 2x equals to 4 plus 2y plus 1. So 2x equals to 2y, and 4 plus 1 is 5. So in total, 2x equals to 2y plus 5. Here we subtract 2y from this equation, and we get that 2x minus 2y equals to 5. Here we take 2 as a common factor from those two expressions. So inside the brackets we have x minus y equals to 5. So in total, if you found out that 2 times x minus y equals to 5, here we divide this equation by 2 and finally get that x minus y equals to 5 over 2. X minus y equals to 5 halves. 5 halves is 2.5. So if you found out that x minus y equals to 2.5. What is the length of the line segment CN? From the drawing it is very easy to see that CN in total equals to CB minus NT minus TB. Again, CN equals to CB minus NT minus TB. So I write it down. CN equals to CB minus NT minus TB. And again, CN in total equals to CB minus NT minus TB. So CN equals to CB. CB is the radius of the big semicircle. That equals to x according to our definition. CB equals to x minus NT. NT equals to y minus TB. TB equals to 1 unit in its length according to what is given as the question. So in total, we actually found out that Cn equals to x minus y minus 1. But x minus y is 2.5. Therefore, we substitute x minus y here by 2.5, and we get that Cn in total equals to x minus y is 2.5 minus 1. 2.5 minus 1 is 1.5. So in total, we actually found out that Cn equals to 1.5 units in its length. This is 97 Cn, that equals to 1.5 units in its length. In our drawing, we have an internal notch between the small circle and the big semicircle. that is to say they touch each other internally, and this point K. Whenever you have an internal edge between two circles or semicircles, you can implement rule 9. So I repeat quickly on rule 9, and we will implement the rule in our drawing. According to rule 9, if two circles touch each other internally, then the straight line that connects their centers together passes through their touching point. Again, if two circles touch each other internally, then the straight line that connects their centers together passes through their touching point. In the drawing, we have two circles. The center of this big circle is here at point O. The center of this small circle is here at point M. The straight line that connects their centers together is of course the straight line OM. And this straight line OM must pass through their touching point, that's actually point P. Again, the straight line OM that connects their centers together must pass through point P, that is their touching point, according to this rule, rule 9. Or OMP is one straight line. Again, OMP is one straight line. So we can implement rule 9 in our drawing. So as I mentioned before, we have an internal edge between the small circle and the big semicircle, and this point K. Point K is their touching point. The center of this big semicircle is here at point C. The center of this small circle is here at point O. The straight line that connects the centers together is of course the straight line CO, and the straight line CO must pass through their touching point, that is point K. Again, according to rule 9, the straight line CO that connects the centers together pass through point K, that is their touching point. Or COK is one straight line. Again, according to rule 9, COK is one straight line. So we join points C and O together by a straight line, and according to rule 9, the straight line CO must pass through point K, that is their touching point. So from the moment it's very easy to see that indeed the straight line CO that connects the centers together passes from point K, that is their touching point. Or COK is one straight line. According to rule 9, COK is one straight line. If COK is one straight line, it means that CO must be equal to CK minus OK. Again, CO must be equal to CK minus OK. So I write it down. CO must be equal to CK minus OK. So CO, this is 97 CO, that equals to CK. CK is the radius of the semicircle, that is X, minus OK. OK is the radius of this small circle, that equals to 1 unit in its length. So in total we found out that CO equals to X minus Y. This is 97 CO, that is equals to X minus Y. But we have already found out that X minus Y equals to 2.5. Therefore CO that equals to X minus Y equals to 2.5 units in its length. We have already found out that this is line segment CN that equals to 1.5 units in its length, and this is line segment ON that is the radius of the small circle that equals to 1 unit in its length. In the next step, I'll copy the right triangle OCN in a new page, and we will implement the Pythagoras theorem on this right triangle, triangle OCN. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Here by PT is the abbreviation for Pythagoras theorem. So actually, this is the right triangle OCN that I copied from the original drawing. In this right triangle OCN, according to the Pythagoras theorem, OC squared, that is the square of the hypotenuse, equals to ON squared plus NC squared. So I write it down. OC squared, that is the square of the hypotenuse, equals to ON squared plus CN squared. OC equals to 2.5 units in its length, therefore OC squared is 2.5 squared, that is 6.25, and is equals to ON squared. ON is y, therefore ON squared is y squared plus CN squared. CN is 1.5, therefore CN squared is 1.5 squared, that is 2.25. So in total we shall find out that 6.25 equals to y squared plus 2.25. Here we subtract 2.25 from this equation, and we get that 6.25 minus 2.25 is 4, so 4 equals to y squared. Here we will take a root out of this equation, and finally get that y equals to the square root of 4, that is 2. So if you found out that the radius of the small circle y equals to 2 units in its length. We have only found out that x minus y equals to 2.5, but y is 2, therefore x minus y is x minus 2, is equals to 2.5. Here we will add 2 to this equation, and we get that x equals to 2.5 plus 2 is 4.5. 4.5 is 9 over 2. So if you found out that the radius x of the big semicircle equals to either 9 over 2 units in its length, or in terms of numbers, the radius x equals to 4.5 units in its length. Our task is to find out the area of this green shape. So what is the area of the green shape? From the drawing it is very easy to see that the area of the green shape equals to the area of the big semicircle minus the area of the small circle. So it is down, the area of the green shape in total equals to the area of the big semicircle minus the area of the small circle. What is the area of the big semicircle? The radius of the big semicircle is x, therefore the area must be equal to pi x squared over 2. The area of the big semicircle equals to pi x squared over 2 minus the area of the small circle. The radius of the small circle equals to y, therefore the area of the small circle must be equal to pi y squared. The radius x of the big semicircle equals to 9 over 2, therefore x squared is 9 over 2 squared. So in total this expression equals to pi over 2 and x squared is 9 over 2 squared minus pi y squared. Y is 2, therefore y squared is 2 squared, that is 4. So in total this expression equals to 4 pi. Here we will open the brackets of this expression and we get that pi over 2 times 9 over 2 squared. 9 over 2 squared equals to 9 squared, that is 81, over 2 squared, that is 4, minus 4 pi. So here we have in the numerator of this expression 81 pi over 2 times 4 is 8. So in total we found out that the area of the big semicircle equals to 81 pi over 8 square units in its size, minus the area of the small circle, that is 4 pi. So here we will multiply minus 4 pi by 8 and then we will divide it by 8 in order to have a common factor of this expression, and we get that minus 4 pi times 8 is minus 32 pi divided by 8. 81 pi minus 32 pi is 49 pi over 8. 49 pi over 8 is 19.24 square units. So if you found out that the area that we are looking for in this question, that is the area of this green shape, it is equals to either 49 pi over 8 square units in its size, or in terms of numbers, the area of this green shape equals to 19.24 square units in its size. So we finish with the first question. In the next step, I will present you the second question, and we will solve the second question of this lecture. Our task in the second question is to find out the length of this line segment PQ that is equals to x. We have to find out the value of x. So in the drawing, we have a semicircle. This is point O, that is the center of this semicircle according to what is given in the question. This is line segment OS, that is equals to 2 units in its length. This is line segment SB, that is equals to 1 unit in its length. This is line segment PT, that is equals to line segment TS. So if we define the length of line segment PT as A, then the length of line segment TS must be also equal to A, because they are equal to each other. In the next step, we will complete this semicircle to a circle. So completed the semicircle to a circle, and we will extend line segment TS by a straight line until it touches the circle. and we will define the touching point of the extended line 70s with this circle. This point is point M. In the next step, we will join points P and M together by straight line. By joining points P and M, we can deal peripheral angle PTM. This is peripheral angle PTM. According to what is given as the question, peripheral angle PTM equals to 90 degrees in its size. And peripheral angle PTM subtend on chord PM. Again, peripheral angle PTM subtend on chord PM. So here we can implement rule 5. I'll repeat quickly on rule 5. According to rule 5, any peripheral angle that is equal to 90 degrees in its size must subtend on the diameter of the circle. So in the drawing we have a circle. This is peripheral angle MAN that is equal to 90 degrees in its size, and therefore according to this rule 5, peripheral angle MAN must subtend on the diameter of the circle. And indeed peripheral angle MAN subtend on MN, that is the diameter of this circle. So according to this rule 5, any peripheral angle that is equal to 90 degrees in size must subtend on the diameter of the circle. We can implement rule 5 in our drawing. One put in our drawing, we have peripheral angle PTM that is equal to 90 degrees in size according to what is given as the question, and therefore peripheral angle PTM according to rule 5 must subtend on the diameter of the circle. Peripheral angle PTM subtend on chord PM, and therefore according to rule 5, chord PM must be the diameter of the circle. So write it down. If we found out that chord PM is the diameter of the circle according to rule 5. It is given as the question that point O is the center of this circle. Point O is the center of the circle, point B is the point of the circle itself, therefore OB is the radius of this circle. OB equals in total to OS plus SB. So OB equals to OS, that is 2, plus SB, that is 1. So in total, OB equals to 2 plus 1, that is 3. So if we found out that the radius of this circle equals to 3 units in its length. So the radius OP equals to 3 units, and the radius OM also equals to 3 units in its length. In the next step, we will do a construction. That is to say, from this point S, we will draw perpendicular on the diameter PM. Again, from point S, we will draw perpendicular on the diameter PM. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point S and the diameter PM. This point is point N. Those two angles are defined as vertex angles, and we know that vertex angles are equal to each other. So if we define the size of this angle as alpha, then the size of this angle must be also equal to alpha because they are equal to each other. In the right small triangle S and O, right lower triangle S and O, this angle equals to alpha, this angle equals to 90 degrees, and therefore this third missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees, that is the sum of the angles in any triangle. Likewise, we focus on the upper right triangle PQO. This right triangle PQO, this angle equals to alpha, this angle equals to 90 degrees, and therefore this third missing angle must be equal to 90 degrees minus alpha, according to the sum rule that the sum of the angles in any triangle is equal to 180 degrees. those two triangles, they are similar to each other according to angle similarity rule. That is to say, the right upper triangle PQO is similar to the right lower triangle, this triangle ONS. So why those two right triangles are similar to each other? First of all, those two angles are both equal to alpha, therefore they are equal to each other. In addition, both those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees and therefore they are equal to each other. So if you found out that all the three angles of this right upper triangle PQO are correspondingly equal to all the three angles of this right lower triangle ONS, and therefore those two right triangles are similar to each other according to angle similarity rule. So I write it down. We actually found out that the right upper triangle PQO is similar, this is the sign of similar, to the right lower triangle ONS, according to angle similarity rule. Okay, again, we found out that the right upper triangle PQO is similar to the right lower triangle ONS according to angle similarity rule. And for the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side SN of the right lower triangle OSN over side PQ of the upper right triangle PQO equals to side OS of the right lower triangle ONS over side PO of the upper right triangle PQO. Okay, again, from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side SN of the lower right triangle ONS or side PQ of the upper right triangle PQO is equals to side OS of the lower right triangle ONS or side PO of the upper right triangle PQO. NS is the missing side, so we leave it as it is. So it is SN over PQ. PQ is the line segment that we are looking for in this question, and it is equals to x. We have to find out the value of x. And it is equals to OS. According to what is given as the question, OS equals to 2 units in its length over PO. We already found out that PO is the radius of this circle, that equals to 3 units in its length. So in total we should find out that Sn over x equals to 2/3. Here we will multiply this equation by x, and we get that the missing side Sn is equal to 2/3 x. This is the missing side Sn, that is equals to 2/3 x. So it is now found out that Sn equals to 2/3 x. In the next step, we define this angle, the size of this angle, as beta, and we'll focus on the right small green triangle S and M. This right green triangle S and M. This green triangle S and M. This angle equals to beta, this angle equals to 90 degrees, and therefore this third missing angle must be equal to 90 degrees minus beta. Why? Because 90 degrees minus beta plus beta is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in a triangle. Likewise, we'll focus on the big right triangle PTM. On the big right triangle PTM, this angle equals to beta, and therefore angle beta is a common angle that belongs to both triangles. Angle beta belongs to the green triangle S and M, and angle beta also belongs to the big right triangle PTM. So in the right big triangle PTM, this is angle beta. This angle equals to 90 degrees, and therefore this first missing angle must be equal to 90 degrees minus beta, according to the sum rule that the sum of the angles in any triangle is equal to 180 degrees. In the next step, we prove that the big right triangle PTM is similar to this green triangle, triangle SNM. So why those two triangles are similar to each other? First of all, this is angle beta, that is a common angle that belongs to both triangles, so we can write now that the angle beta equals to itself is a common angle that belongs to both triangles. In addition, those two angles are both equal to 90 degrees, and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus beta, therefore they are equal to each other. So we shall prove that all the figures of this big right triangle PTM are corresponding equal to all the figures of this small green triangle S and M. And therefore those two right triangles are similar to each other according to angle similarity rule. So I did not, we shall find out that the big right triangle PTM is similar. This is the sign of similar to this right green small triangle S and M according to angle similarity rule. And again, we found out that the big right triangle PTM is similar to the right small green triangle SNM according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side SN of the green small triangle SNM over side PT of the green on side PT of the big right triangle PTM equals to side SM of the green small triangle SNM over side PM of the big right triangle PTM. So repeat again, from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side SN of the green small triangle SNM over side PT of the big right triangle PTM is equal to side SM of the green small triangle SNM over side PM of the big right triangle PTM. We have already found out that Sn equals to 2/3 x over pt. Pt equals to a units in itself according to our definition, and it is equals to Sm. Sm is the missing side, so we leave it as it is, over Pm. Pm is the diameter of the circle. The radius of the circle is 3, therefore the diameter is 3 plus 3, that is 6. So in total, we found out that 2/3 x over a equals to sm over 6. Here we will first multiply this equation, and finally we get that 2/3 x times 6 equals to a sm. This is equation 1. Turn into equation 1, and we found out that 2/3 x times 6 equals to ASM. Here we have 6 over 3 is 2, and 2 times 2x is 4x. So in this side of this equation 1, we have 4x. And 4x equals to ASM. And together we found out that according to equation 1, x equals to ASM. In the next step, I will present to you all 15, and we will implement all 15 in our drawing. We already talked about all 15 in the previous lecture, so I'll repeat on all 15 quickly, and we will implement all 15 in our drawing. According to all 15, if chord AB intersects with chord CD at point O, then the following equation is true, that AO times OB equals to CO times OD. So in the drawing we have a circle. This is chord AB that intersects with chord CD at point O. Again, chord AB intersects with chord CD at point O. So in this drawing, the following equation is true, that AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. So we can actually implement all 15 in our drawing. Why? Because in our drawing we have chord TM that intersects with chord AB at point S. Again, chord TM intersects with chord AB at point S. So all the requirements for all 15 are satisfied, and therefore we can implement here all 15. So I'll write it down. In our original drawing, we have chord TM that intersects with chord AB at point S. The intersection point occurs at point S, this point. And again, in our original drawing, chord TM intersects with chord AB at point S. So we can implement all 15. According to all 15, the following equation will be true, that TS times SM equals to AS times SB. Again, TS times SM equals to AS times SB. So as you know, TS times SM equals to AS times SB. Okay, again, according to all 15, the following equation is true, that TS times SM equals to AS times SB. TS equals to A, SM is the missing side, so in this side of this equation 2 we have A times SM, and it is equals to AS. What is the length of AS? AS in total equals to AO plus OS. So AS equals to AO. AO is the radius of this circle, that is equals to 3, plus OS, that is 2. So in total, AS equals to 3 plus 2, that is 5. AS equals to 5 times SB. SB equals to 1 unit in itself according to what is given to the question. So in total, if you found out that according to equation 2, A times SM equals to 5 times 1. 5 times 1 is 5. So in total, according to equation 2, if you found out that A times SM equals to 5, this is according to equation 2. While according to equation 1, we already found out that A times SM equals to 4x. According to equation 1, A times SM equals to 4x. So actually, we have two different equations for the expression A times SM. Therefore, we get the equation 3 that states that A times SM according to equation 1 must be equal to A times SM according to equation 2. Repeat again, equation 3 states that A times SM according to equation 1 must be equal to A times SM according to equation 2. A times SM according to equation 1 equals to 4x, and it must be equal to A times SM according to equation 2. A times SM according to equation 2 equals to 5. So in total, according to equation 3, we have found out that 4x equals to 5. Here we divide this equation 3 by 4, and we get that x equals to 5 quarters. 5 quarters is 1.25. So if we found out that the length of this 97 p cubed is equals to x, it is equals to either 5 quarters units in itself, or in terms of numbers, the length of line segment p cubed is equals to x is equal to 1.25 units in its length. And again, PQ is equals to x, it is equal to either 5 quarters units in its length, or in terms of numbers, it is equals to 1.25 units in its length. And that is the answer to the second question. So in the next step, I'll summarize the lecture. We start with the first question, of course. In the first question, our task was to find out the area of this green shape. So in the drawing, we have this small circle inside this big semicircle. We also know that AQ equals to 4 units in its length. This is 970B, that is equals to 1 unit in its length. This is again PQA, that is right angle. This is again STB, that is also right angle. Again, our test is to find out the area of this green shape. So first of all, we define the radius of this big semicircle as x and the radius of this small circle as y. In addition, we define the center of this small circle, this point is point O, and we define the center of this big semicircle, this point is point C. We also define the point of tendency of tangent AB with this small circle, this point is point N. Likewise, we define the point of tendency of tangent PQ with this small circle, this point is point H. We define the point of tendency of tangent ST with this small circle, this point is point L. And finally, we define the attachment point of this small circle with this big semicircle, this point is point K. In the next step, we join points O and N together by a straight line. Point O is the center of this small circle, point N is the point of the small circle itself, therefore ON is the radius of this circle. This is equal to 1 unit in itself, according to our definition. the radius ON is equals to y, the radius ON is drawn to point N, that is the point of tendency of tangent A and B with this small circle. And whenever your radius that is drawn to the point of tendency, then tangent A and B will be perpendicular to the radius NO. If tangent A and B is perpendicular to NO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to all 1. This is angle PQA, that is the right angle. According to what is given in the question, AB is the diameter of this semicircle. AB is the diameter, it is absolutely a straight line. So if you focus on the upper side of the straight line AB at point Q, here the sum of the angles must be equal to 180 degrees according to all three. All three states that the sum of the angles from one side of a straight line is equal to 180 degrees. So which angles here at the upper side of the straight line AB at point Q? We have this angle that is the right angle, plus this missing angle. In total the sum of those two angles must be equal to 180 degrees according to all three. Therefore, this missing angle must be equal to 90 degrees in its size. Likewise, if you focus on the upper side of the straight line AB at point T, here the sum of the angles must be equal to 180 degrees according to all three. So which angles we have at the upper side of AB at point T? We have this angle that is the right angle according to what is given as the question, plus this missing angle. In total the sum of those two angles must be equal to 180 degrees according to all three. Therefore this missing angle must be equal to 90 degrees in its size. So in the next step, we join points O and H together by straight line. OH is of course the radius of this small circle that equals to y. The radius of OH that is equal to y. The radius of OH is drawn to point H, that is the point of tendency of tangent PQ with this small circle. And whenever your radius is drawn to the point of tendency, then tangent PQ will be perpendicular to the radius HO. If PQ is perpendicular to HO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. So in quadrilateral OHQN, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this 4-facing angle. In total, they must be equal to 360 degrees according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore, this 4-facing angle must be equal to 90 degrees in its size. So inside quadrilateral HOQN, we have 4 right angles. And according to rule 5, any quadrilateral that has 4 right angles must be a rectangle if not a square. So we relate to quadrilateral HO and Q is a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle HO and Q, side HO must be equal to the opposite side NQ. But HO is y, therefore the opposite side NQ must be also equal to y unit in its length. In the next step, we join points O and L together by a straight line. OL is of course the radius of this circle, the radius of the small circle that is equals to y. So OL that is equals to y, OL is drawn to point L, that is the point of tendency of tangent ST with this small circle. And whenever your radius that is drawn to the point of tendency, then tangent ST will be perpendicular to the radius LO. If ST is perpendicular to LO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to the sum rule 1. So inside quadrilateral OLTN, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this 4-facing angle, total the must be equal to 360 degrees according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore this 4-facing angle must be equal to 90 degrees in its size. So inside quadrilateral OLTN, we have 4 right angles. And according to rule 5, any quadrilateral that has 4 right angles must be this rectangle if not a square. So we go to quadrilateral OLTN as a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle OLTN, side OL must be equal to the opposite side TN. But OL is y, therefore the opposite side TN must be also equal to y units in its length. So in total, QT equals to y plus y, that is 2y. QT is a straight line because it is part of the straight line AB. Again, QT is part of the straight line AB, therefore it must be also a straight line. So QT in total equals to y plus y, that is 2y. AB is the diameter of the semicircle, therefore it's twice as long. It is twice as long as the radius. The radius of the semicircle is x, therefore the diameter must be equal to 2x. So the diameter AB, from one side it is equals to 2x, but from the other side, AB also equals to AQ plus QT plus TB. Again, AB in total equals to AQ plus QT plus TB. So from the other side, AB also equals to AQ plus QT plus TB. AQ is 4, QT is 2y, and TB is 1. Again, AQ is 4, QT is 2y, and TB is 1. So in total, 2x equals to 4 plus 2y plus 1. So 2x equals to 2y, and 4 plus 1 is 5. So in total, 2x equals to 2y plus 5. Here, we subtracted 2y from this equation. If I found out that 2x minus 2y equals to 5. Here, we took 2 as a common factor from those two expressions. So inside the brackets, we left with x minus 5. So in total, we should found out that 2 times x minus y equals to 5. Here, we divided this equation by 2, and finally found out that x minus y equals to 5 halves. 5 halves is 2.5. So x minus y equals to 2.5. What is the length of this 9/7 Cn? From the law, it is very easy to see that Cn in total equals to Cb minus Nt minus Tb. Again, Cn in total equals to Cb minus Nt minus Tb. So Cn equals to Cb. Cb is the radius of the semicircle, that is x, minus Nt. Nt is y, and Tb is 1. So in total, Cn equals to x minus y minus 1. X minus y is 2.5, therefore we substitute x minus y by 2.5. So in total, we should find out that Cn equals to 2.5 minus 1, that is 1.5. So in total, we should find out that the length of this line 7 Cn equals to 1.5 units in its length. So in our drawing, we have an internal notch between this small circle and this big semicircle. That is to say, they touch each other internally in this point K. Therefore, we can implement here rule 9. Whenever you have an internal notch between two circles or semicircles, you can implement rule 9. So repeat quickly on rule 9. According to rule 9, if two circles touch each other internally, then the third line that connects the circles together passes through their touching point. Again, if two circles touch each other internally, then the third line that connects the circles together passes through their touching points. In the drawing, we have two circles. This is the big circle with the center O. This is the small circle with the center M. The third line that connects the circles together is of course the third line OM. And according to this rule 9, the third line OM must pass through their touching point, that is point P. Again, the third line OM must pass through their touching point, that is point P. Or the third line OM must pass through point P, that is their touching point. Or O and P is one third line. Again, O and P is one third line according to this rule 9. So we can actually implement rule 9 in our drawing. Why? Because in our drawing we have an internal notch between the small circle and the big semicircle and point K. The center of this big semicircle is at point C. The center of this small circle is at point O. The third line that connects the circles together is of course the third line OC. And this third line OC must pass through their touching point, that is point K. Again, the third line OC must pass through point K, that is their touching point. Or OCK is one third line. Again, COK is one third line according to rule 9. If COK is one third line, it means that CO must be equal to CK minus OK. Again, CO must be equal to CK minus OK. So CO equals to CK. CK is the radius of the semicircle, that is x, minus OK. OK is the radius of the small circle, that is y. So in total, we should find out that CO equals to x minus y. This is 9/7 CO. That is equals to x minus y units in its length. But we already found out that x minus y equals to 2.5. Again, x minus y equals to 2.5. Therefore, CO that is equals to x minus y is equals to 2.5 units in its length. We already found out that Cn equals to 1.5 and On is the radius of this small circle, that is y. So in the next step, I copied the right triangle OCN in a new page and implemented the Pythagoras theorem on this right triangle OCN. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So actually, this is the right triangle OCN that are coming from the original domain. In this right angle OCN, according to the Pythagorean theorem, OC squared, that is the square of the hypotenuse, must be equal to ON squared plus NC squared. OC is 2.5, therefore OC squared is 2.5 squared, that is 6.25, and it is equal to ON squared. ON is y, therefore ON squared is y squared, plus Cn squared. Cn is 1.5, therefore Cn squared is 1.5 squared, it is 2.25. So in total we should find out that 6.25 equals to y squared plus 2.25. Here we subtract 2.25 from this equation and find out that 6.25 minus 2.25 is 4, so 4 equals to y squared. Here we took a root out of this equation and found out that y equals to the square root of 4, that is 2. So the radius of the small circle y equals to 2 units in its length. We only found out that x minus y equals to 2.5, but y is 2, so x minus y is x minus 2, that is equals to 2.5. Here we added 2 to this equation and found out that x equals to 2 plus 2.5, that is 4.5. 4.5 is 9 over 2, so I should find out that the radius of the big semicircle x equals to either 9 over 2 square units, 9 over 2 units in its length, or in terms of numbers, x equals to 4.5 units in its length. Our test is to find out the area of this green shape. So what is the area of the green shape? The area of the green shape equals to the area of the big semicircle minus the area of the small circle. Repeat again, the area of the green shape is equals to the area of the big semicircle minus the area of the small circle. The radius of the small circle, the radius of the big semicircle is x, therefore the area of the semicircle must be equal to pi x squared over 2. Minus the area of the circle, the radius of the small circle is y, therefore the area of the small circle must be equal to pi y squared. X is 9 over 2, therefore x squared is 9 over 2 squared. So in total this expression equals to pi over 2 times 9 over 2 squared minus pi y squared. Y is 2, so y squared is 2 squared, that is 4. So in total this expression equals to 4 pi. We open the brackets of this expression and found out actually that pi over 2 times 9 over 2 squared. 9 over 2 squared equals to 9 squared, that is 81, over 2 squared, that is 4. So in total this expression equals to 81 pi over 2 times 4, minus 4 pi. So this expression equals to 81 pi over 2 times 4 is 8. So in total the area of the semicircle equals to 81 pi over 8 square units in its size, minus 4 pi. Here we multiplied minus 4 pi by 8 and then we divided by 8 in order to come out of this expression. Minus 4 pi times 8 is minus 42 pi over 8. 81 pi minus 42 pi is 49 pi over 8. So if you found out that the area of this green shape, that is the area that we are looking for in this question, it is equals to either 49 pi over 8 square units in its size, or in terms of numbers, the area of this green shape equals to 19.24 square units in its size. So we finish with the first question. In the next step I can do the second question and we solve the second question of this lecture. In the second question, our task is to find out the length of this line segment PQ that is equals to x. We have to find out the value of x. So in the domain we have a semicircle. Point O is the center of this semicircle. This is line segment OS that is equals to 2 units in its length. This is line segment SB that is equals to 1 unit in its length. This is angle PTS, that is right angle. This is angle PQ. B, that is also right angle. Again, our task is to find out the length of this line segment PQ that is equals to x. We have to find out the value of x. It is given us the question that PT equals to TS. So if we define the length of line segment PTSA, then TS must be also equal to A because they are equal to each other. In the next step, we completed this semicircle to a circle. And we extended line 70s by side line until it touches the circle. We define the touching point of the extended line 70s with this circle. This point is point M. Then we join points P and M together by side line. By doing all those constructions, we're going to do peripheral angle PTM. This is peripheral angle PTM. That is equals to 90 degrees in size. And peripheral angle PTM sub 10 on chord PM. Again, peripheral angle PTM sub 10 on chord PM. And according to rule 5, any peripheral angle that is equals to 90 degrees in size, like this peripheral angle, must subtend on the diameter of the circle. following PTM that is the right angle, subtend on chord PM, and therefore according to rule 5, PM must be the diameter of the circle. PM is the diameter of the circle according to rule 5. In the next step, we did a construction, that is to say from point S, we do perpendicular on the diameter PM. Again, from point S, we do perpendicular on the diameter PM. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point S and the diameter PM. This point is point N. Those two angles are defined as vertex angles, and we know that vertex angles are equal to each other. So if we define the size of this angle as alpha, then the size of this angle must be also equal to alpha because they are equal to each other. So in the right triangle ONS, this angle equals to alpha, this angle equals to 90 degrees, and therefore this missing angle, this third missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees, that is the sum of the angles in a triangle. Likewise, in the upper right triangle PQO, this angle equals to alpha, this angle equals to 90 degrees, and therefore this first missing angle must be equal to 90 degrees minus alpha according to the sum rule that the sum of the angles in a triangle is equal to 180 degrees. In the next step, we prove that those two right triangles are similar to each other according to angle similarity rule. That is to say, those two angles are both equal to alpha, therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees, and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So if we prove that all the figures of this upper right triangle PQO correspond equal to all the figures of this lower right triangle ONS, and therefore those two right triangles are similar to each other according to angle similarity rule. So if we follow that the upper right triangle PQO is similar, this is the sign of similar, to the right lower triangle ONS according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side SN of the right lower triangle ONS over side PQ of the upper right triangle PQO is equals to side OS of the right lower triangle OSN over side PO of the upper right triangle PQO. And we derive that SN over PQ equals to OS over PO. SN is the missing side, so leave it as it is, over PQ. PQ is the line segment that we are looking for in this question, and it is equals to x. We have to find out the value of x. SO is 2 and PO is 3. So in total, we found out that SN over x equals to 2/3. Here we multiply this equation by x and found out that the missing side SN equals to 2/3 x. Again, SN equals to 2/3 x. This is the missing side SN. That is equals to 2/3 units, 2/3 x units in its length. In the next step, we define the size of this angle is beta, and we focus on the green small triangle SNM. So this angle equals to beta, this angle equals to 90 degrees, and therefore this first missing angle must be equal to 90 degrees minus beta. Why? Because 90 degrees minus beta plus beta is 90 degrees, and 90 degrees plus 90 degrees, it is equals to 180 degrees, that is the sum of the angles in a triangle. Likewise, in this big right triangle PTM, this is angle beta, therefore angle beta is a common angle that belongs to both triangles. So this is angle beta, this angle equals to 90 degrees, and therefore this first missing angle must be equal to 90 degrees minus beta according to the sum rule that the sum of the angles in a triangle is equal to 180 degrees. In the next step, we prove that the big right triangle PTM is similar to this green small triangle SNM. So why those two right triangles are similar to each other? First of all, this is angle beta, this is a common angle that belongs to both triangles. So we can write down that angle beta equals to itself as a common angle that belongs to both triangles. In addition, those two angles are both equal to 90 degrees and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus beta, therefore they are equal to each other. So if we prove that all the figures of this big right triangle PTM correspond equal to all those three angles of this green small triangle NSM, and therefore those two right triangles are similar to each other according to angle similarity rule. So if we found out that the big right triangle PTM is similar, this is the sign of similar, to the right small triangle SNM, to the right small green triangle SNM, according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side SN of the green triangle SNM over side PT of the big right triangle PTM is equals to side SM of the green triangle SNM over side PM of the big right triangle PTM. And again we derive that SN over PT equals to SM over PM. We already found out that SN equals to 2/3 X over PT. PT equals to A, and it is equals to SM. SM is the missing side, so we leave it as it is, over PM. PM is the diameter of the circle that is twice as long as the radius. The radius is 3, therefore the diameter is 6. So PM equals to 6. PM equals to 6. So in total we should find out that according to equation 1, 2/3 X over A equals to SM over 6. Here we cross multiply this equation and find out that 2/3 X times 6 equals to ASM. 6 over 3 is 2 and 2 times 2x is 4x. So in total on this equation 1 we have 4x, so 4x equals to ASM. Repeat again, we found out that according to equation 1, 4 times x equals to ASM. So we can implement rule 15 in our drawing. So implement quickly on rule 15 and implement rule 15 in our drawing. According to rule 15, if chord AB intersects with chord CD at point O, then the following equation is true, that AO times OB equals to CO times OD. So in the drawing we have a circle, this is chord AB that intersects with chord CD at point O. So in this drawing the following equation is true, that AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. So we can definitely implement all 15 in our drawing. Why? Because in our drawing we have chord TM that intersects with chord AB at point S. Again, chord TM intersects with chord AB at point S. So all the requirements of rule 15 are satisfied, and therefore we can implement rule 15. So again, in our original drawing, chord TM intersects with chord AB at point S. The intersection point occurs at this point S. So we can implement rule 15. According to rule 15, the following equation is true, that TS times SM equals to AS times SB. Again, TS times SM equals to AS times SB. And again, according to rule 15, the following equation is true, that TS times SM equals to AS times SB. TS is A times SM. SM is the missing sign, so we leave it as it is. So on this side of the equation 2 we have ASM and it is equals to AS. AS in total equals to AO plus OS. AO is the radius, that is 3, plus OS, that is 2. So in total AS equals to 3 plus 2, that is 5. And SM is 1. So again, AS is 5 and SB is 1. SB is 1. So in total we should find out that according to equation 2, A times SM equals to 5 times 1. 5 times 1 is 5. So in total according to equation 1, according to equation 2, we should find out that 8 times SM equals to 5. This is according to equation 2, and according to equation 1, we have already found out that 8 times SM equals to 4x. So we have two different expressions for ASM. Therefore we get the equation 3 that states that ASM according to equation 1 must be equal to ASM according to equation 2. Again, according to equation 3, ASM according to equation 1 must be equal to ASM according to equation 2. ASM according to equation 1 equals to 4x, and it must be equal to ASM according to equation 2. ASM according to equation 2 equals to 5. So in total according to equation 3, we actually found out that 4x equals to 5. Here we divided this equation 3 by 4, and finally found out that x equals to 5 quarters. 5 quarters is 1.25 units. So we should find out that the length of this line segment PQ that equals to x, it is equals to either 5 quarters units in its length, or in terms of numbers, the length of this line segment PQ that is equals to x is equal to 1.25 units in its length. Okay, thank you very much.